Introduction to Mathematical Proofs. Today we're going to be talking about conjunctions and tables. So at the beginning we're going to learn some grammar, and then after that we're going to learn about tables. Okay, I'm kidding about the tables part, but the grammar actually does make sense. So a conjunction is a word that connects two clauses. For example, I ate a cookie and drank some milk uses and as a conjunction to connect the two phrases or clauses, I ate a cookie and the clause drank some milk. Another example is you can choose the red pill or the blue pill. This uses or as the conjunction. And these are the only two that we're going to need for our cases in math. But there are some other ones. For example, but is literally one, whereas, after, these also work as conjunctions. And maybe you can see why this comes in handy. We can chain mathematical statements together with these two conjunctions, right? And we'll get a different mathematical statement. So for example, all primes are either odd or the number 2. So if you were to just say all primes are odd, that's false. Or if you were to say all primes are the number 2, that's also false. Using the or, which is doing the heavy lifting, you're combining the primes are odd or the number 2 together. And now this statement is true. We're producing a completely new statement. Just like if you have two clauses, each one of them might be a sentence, but then together when you combine them with a conjunction, it becomes a new sentence entirely. So this statement is actually now true. And here's another one. All integers are even and greater than 0. Here, and means that both of them have to be true. And this is not true. All integers are not even and greater than 0. For example, 1 is an integer, but it's not even, but it is greater than 0. So there are many ways that you can disprove an and. You'd have to show that either one doesn't hold. So an or, what this means is that either one of them can be true, and thus the whole statement is true. And you need both of them to be true. It's kind of like how English works. And let's just run through two simple proofs of all primes are either odd or the number 2. So what's interesting here is like, okay, how do you prove this? Well, you have to prove either one of the two things, either that all primes are odd or all primes are the number 2. So for the first proof, we're going to assume P to be a prime and not equal to the number 2. So we're completely discluding the possibility that it's the number 2. So like, okay, fine, we'll make it not be the number 2, then we'll show that it must be an odd one. And here we can just run through the proof. Since P is prime, it isn't divisible by any numbers other than P and 1. And P isn't divisible by 2, but since P is not equal to 2, we must have that P can't be even. Because if it were even and not equal to 2, then it'd be divisible by 2, right? You see how it kind of creates circular logic. So P must be odd. Or the other thing we can do is say, okay, all primes are either odd or the number 2. Well, let's say it's not odd. Let's say it's even. Then we'll show that it's the number 2. So let P be an even prime. Then P is equal to 2k for some k. Then, if k is greater than 1, we can divide P by 2 and it wouldn't be a prime. So we must have that k is 1. And notice here that if k is negative, P would be a negative number, but we only talk primes in the sense of natural numbers. And if k is equal to 0, P is equal to 0, that's not a natural, it's not prime. So P must be equal to 2. So you should see what's happening here. Pretty much, we can show that one of the conditions, either condition 1 or condition 2, is false, and then show that the other one must be true. The or is doing a lot of heavy lifting. Remember, we're proving that condition 1 or condition 2 is true. So if we assume that one of them is false, all we have to do is show that the other one is true. Let's just look at symbols. The right side up triangle, the one pointing up means and the one pointing down means or. These look pretty similar to the set operations, intersection and union. So if that helps you, you can kind of think of them together. And the nice thing about these symbols is that we can also use them in set builder, because the right hand side of any set written in set builder kind of acts like a mathematical statement. For example, if you consider the set A is equal to x, where x is an integer and x is greater than 3 and x is even, how can you turn the right hand into just symbols? Well, you just do it as such. X is in the integer, so x is an element of z, the set of integers, and so we use the pointing up triangle. X is greater than or equal to 3, and it's pointing up, there exists a k, or that's an integer, so that can be written as 2k, so x is equal to 2k. And unlike in English, we can use commas with more than 3 items and just spam more ends. So the reason why this is nice is because when you have everything in symbolic form, there's no ambiguity about what this means. Now we're going to look at one more symbol, the not symbol, or the negation symbol. And it's quite simple. You take the opposite of what's not there. For example, if you want x is not even, we say that there does not exist any integer so that x is equal to 2k. So the not means the opposite of it. So this should make sense. And what's interesting here is that there's also another way to say the exact same thing. You can say that for all k, or for every single integer, x is not equal to 2. So saying there does not exist a k so that something is true is the same as saying for every single k, this thing is false. Let's negate this statement, there exists an x in the integer such that x is prime and x is greater than or equal to 4. Now let's just take this one at a time. The opposite of there exists is for all. So we're going to say for all integers. The opposite of x being prime is that x is composite. And the opposite of x being greater than or equal to 4 is that x is less than 4. But we're missing something. What's the opposite of and? Let's just think about an example here. Let's look at the number 5. X is equal to 5 satisfies the statement above. X is prime and x is greater than or equal to 4. We found an integer so that the statement is true. How would we make this number 5 not true anymore? Well, you don't have to make it composite and less than or equal to 3. You just have to choose one of them. So if we make it 6, for example, that breaks the prime part. So x would, if we have 5, 6 is composite, so this would be true, but it's still greater than or equal to 4. But this x doesn't work because of the way and works. So the opposite of and kind of acts like an or. You can choose either statement to break. So we flip the and into an or. And this is what we call De Morgan's law. So if you let x and y be mathematical statements, then x and y, the negation of that, or the opposite of x and y, is not x or not y. And this is called De Morgan's law. It's pretty important whenever you're thinking about negations or flipping things. And it's kind of hard to think about this if the last example didn't make sense. So we're going to introduce a tool to kind of analyze what this means. So we're going to use something called a truth table to explain how all these work together. We'll let x be a mathematical statement. It doesn't matter what it is, it can be any mathematical statement. And we don't know whether it's true or false, so we'll write out the possibility of x in the table. But right now there's only one column. Ideally, you'd have multiple columns to the right, and then it would depend on what the value of x is. But before we add another column with anything related to x, let's add in another column related to y. So y is another mathematical statement. And once again, we don't know whether this is true or false. We'll have to write out all the possibilities of y in the table. This means that there's two things that x can be true or false, and there's two things y can be, and that's true or false. So when you multiply those together, you get 4 different combinations. So you can either have true, 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 false, false, true, or false, false. And these are the 4 combinations we have. And now we can combine these together. So let's just look at some nice conjunctions. So let's look at x and y. What happens to x and y? Well, if x is true and y is true, then it's true. So true, true. So if x is true, y is true, x and y is true. But if x is true and y is false, then x and y is false, because you need both of them to be true. But if we look at the or, if x is true and y is false, x or y is true, because x is true. I know I'm saying true and false and x and y a lot, but just make sure you understand what the table is saying slowly. Just think about it. We're given all the possibilities of what x and y can be. And then we have ways to connect these mathematical statements together. So we have x and y, and then we have another one, x or y. And the value of x and y depends on what x and y is, and the value of x or y depends on what x and y is. Now we're going to introduce some negations. So not x would be the opposite of x. So because not true is false and not false is true. So not x would just flip the true to false, and not y would flip the y's truth value. So if x is true, not x is false. If x is false, not x is true. Make sure you understand what's happening here. Now, we're going to add in not x and y and not x or y. So all we're going to be doing is looking at what x and y is. If it's true, turn it false. If it's false, turn it true. That's what it means to negate something. And we're going to do the same thing for x or y, and we put that in the table down at the bottom. And now finally, we're going to add our not x and not y's and not x or not y's. If you have not x and not y, well, if not x is false and not y is false, then that's false. If not x is false and not y is true, well, both of them aren't true yet, so that's false. So you need not x to be true and not y to be true, which means you need x and y to be false. And then only then is not x and not y true. And the same thing happens for the or. Once again, I can't really explain it that well because it's just something that you kind of have to understand. If you see it, you see it. If you don't see it, just look at it a little bit longer. Maybe you notice something very interesting. These two columns highlighted in purple are actually the exact same thing. They have the exact same truth value. So we say that they're logically equivalent, or they mean the exact same thing. And maybe you can see the other pair right there. The third column and the last column also have the exact same truth values. So depending on whether x is true and y is true, we can learn about all these other different conjunctions and how they work with their negations. And this is called De Morgan's law. So if you look at here, negating x and y, so if you have x and y and we negate that, that's the same as saying not X or not Y. So let's just run through an example. Let's say you look at a room and you're like, okay, in this room there are 2 chairs and 2 desks. Well, when is that false? Think about when that would be false. Well, it would mean that either there isn't 2 chairs, so that's not X, or there isn't 2 tables, that's not Y. So if you think of X and Y being there's 2 chairs and 2 tables, and the negation of being, okay, when is this false? Then not X is saying, oh, there aren't 2 chairs, and not Y is saying there aren't 2 tables. And then you can understand why the or is there, because if you have 3 tables and 2 chairs, well, then the room doesn't have 2 tables and 2 chairs, but only one of them is false. Yeah, so truth tables are meant to be a tool that helps you understand these things. They're not meant to be like an extra thing that, oh, here's another thing that I'm quizzed on. The idea of a truth table is this another way to understand if something is true or something is false. And this is kind of annoying because if you're not completely on board with the idea of a truth table, or it doesn't make sense to you, or you need to be like, okay, let me think about it this way and then convert it into a truth table, it becomes harder to understand. The truth table is meant to be another way to understand the ideas. So we're going to be using the truth tables a few times in the next few videos, and it's a little annoying. I'm gonna be honest, right? You really don't need to understand what a truth table is to be able to do math, because it doesn't show up. It's just to make you understand the ideas of what is a true statement, what is a false statement. Okay, so that will be it for now. If it doesn't make sense, once again, rewatch the video or just think about it over time. So until then, I will see you later.